Hi, my partner William and I will be talking about our final project, which was on predicting observed gene expression using Enformer and binary classifiers. A problem we are facing today is the fact that it is incredibly difficult to predict gene expression from mutations and determine the effects of genomic variants. Previous work has attempted to discover EQTLs by developing a model upon previously mapped data and analyzing expression modifying variant gene pairs. For example, Wang and his colleagues were able to do this by training a random forest classifier on over 5,000 features that is able to score these features and calculate the expression modifier score. There's also a model called Enformer, which combines state-of-the-art deep convolutional neural networks and transformers. By using attention layers that can integrate information from long-range distance along the sequence, Enformer is able to predict the effects of gene variations. Our goal is to create a classifier that is trained on Enformer predictions and can achieve better performance than the previous work.
The data that we used for models was the same data that was used in Wang et al.'s EMS study. This data was taken from the UK Biobank and contained over 5 million variant gene pairs, along with posterior inclusion probabilities that a given variant would be an EQTL. We then took specific data points that were scored significantly likely and unlikely. We selected data points that were above a certain threshold value of 0.9 to label as true, and data points under a threshold value of 0.01 to label as false. The dataset we used for training ended up being around 3,000 data points, which we then took and inputted into Enformer to obtain their variant effect prediction on gene expression. Each data point was outputted into 5,313 tracks of length 896. These 896 values correspond to 114,688 base pairs. We then took this data and trained all the models with the exact same data.
For this project, we created 3 different models. Our first model is a random forest classifier, which is an ensemble of 97 trees that votes on the classifier's output. Each tree is trained on around 100 data points. Our second model is a fully connected neural network, which is composed of flattened data vectors taken from informal predictions. These vectors are then passed through a hidden layer and an output layer. Lastly, we created a convolutional neural network that's composed of 5 convolutional layers, 5 max pooling layers, and 1 linear output layer. After training these 3 models, we assessed their performance by calculating the prediction accuracy on our test data set. The model's prediction is accurate if given a certain test data, the model's output is greater than 0.5, and the ground truth PIP value is greater than 0.9.
Our 3 models all performed better than the random 50% baseline, with between 63 to 63% accuracy on test sets. Of our 3 models, the CNN achieved the highest prediction accuracy, but only by little. We also calculated the area under the precision recall curve and displayed the confusion matrices on the slide here. Our scores were not able to beat Wang et al.'s EMS scores, but was able to classify true positives very consistently. Of our models, the random forest achieved the greatest score while requiring the least amount of parameters. We believe that the use of Enformer allows long-range information to be captured in the output features, which the random forest was able to capture and make predictions on. However, looking at the confusion matrix on the right, it seems that both the random forest and the fully connected network have a bias towards falsely labeling variant pairs as true, resulting in a lot of false positives, while the CNN does not make as many false positives. Since we trained our models with an equal number of each label, we believe that the models were not able to be trained on real-world priors. In a real-world setting, the CNN may actually perform better since the number of variants that are expressive is much smaller than the number of variants that are not. We were surprised at how well some of our models performed with the help of the Enformer, and although we did not beat Wang et al.'s area under the precision recall curve score, we believe our approach can improve given better feature design. Our biggest obstacle while training our models was the memory problems that we ran into while dealing with Enformer data. Since Enformer outputs a matrix of 5,313 by 896 for each variant gene pair, the 3,000 variant gene pairs that we trained on took up a combined 54 gigabytes.
Our next steps will be to find efficient ways to process the data or set up larger systems to handle a large amount of data. Another avenue of improvement is to focus solely on highly informative features using principal component analysis. This would drastically reduce the required amount of RAM and speed up training. This could also allow us to gather more predictions from Enformer and hence expand our training set, which will eventually generate stronger models. Similarly, we could combine some features used by Wang and his colleagues along with Enformer predictions to have a more comprehensive training set to train our models on.